So the second part of section 4.4 is the net change theorem. So the idea here is very similar to a lot of things we've already been talking about. If we think of f, this big F prime, as the rate of change of f, which that is common, derivatives as rate of change, then the fundamental theorem of calculus part 2, which we talked about in the last section, tells us that this is simply going to be equal to f of b minus f of a. Okay, so no different. But the idea behind it is simply that we're talking about essentially the idea, I mean, you'll see an example here with the idea of velocity. That if you have a position function, then its derivative is velocity, so it would make sense that the antiderivative velocity is the position function. And that can tell us something about the function itself, which in this case is the idea of the total change in the function from one value to another on some interval. Okay. So the idea here is that all the applications of the derivative can now be used here. So things that we've already talked about. Okay, so here's the idea. If you are going to take the integral of the velocity from a to b, what that is called is total displacement. Whereas notice the very small difference here in the second one, you can see that there's absolute value, symbols on each side of that velocity. This would give you total distance. And those two things are different. So for example, look at this picture here. So notice that this is the velocity function, and that what's created underneath the velocity function and the t-axis here is some amount of area. So if we're going to talk about displacement, just taking the integral from a to b, in this case from t1 to t2, it's going to be just like we've talked about before when we talked about area in integration, which is if you just take that integral, you're going to get a1, it's going to subtract because a2 is going to be negative, and then you're going to get an addition of a3. So because the two positive areas, and then you have your area underneath. So that's what's going to happen. That's what the integration is going to do. Now, if you were to find distance, you're going to do the absolute value of the velocity function. Then what that's going to do is that's going to take a1, it's going to add a2, and it's going to add a3. So it's going to give you that total area under the curves, and that is what distance is. So as just like an example here, if you had, say, a person, and that person decides to take a walk, hopefully outside, because it's nice. So this person is going to walk, and then they're going to, so say they're kind of walking around the block here. However, just for purposes of what we're doing, all right, we'll say 40 meters. Okay, 40 meters, and then 2 meters. No, that doesn't make sense for a block. 20 meters, and then this is a rectangle, so 40 meters and 20 meters. So this person is going to walk this direction, they're going to head down, they're going to head back towards where they started, and the displacement of this person, displacement, is what happens when the person is basically back to that starting point. And so because they're going, 40 meters and then 20 meters, but then they're going back towards where they started, their displacement is actually the idea of 0. Now, the distance the person traveled, we can see, is the person went 40 meters, and then another 20, and then another 40, and then another 20. So, a pretty big difference here, that this person went 120 meters in terms of their distance, but their displacement is 0 because they're back where they started when they're done. Another example of where this could come up besides displacement and distance is, for example, the total change in cost. So that very basic idea of business things that we don't see that much. But the total change in cost is production level goes from A to B. And again, total change, right? So that's the idea behind this. I moved it down to the bottom here just for space. So not surprisingly, just using from what we have above, that's going to be C of B minus C of A, because inside the integral is that derivative of C. You know, it's marginal cost. So when you take the antiderivative of the derivative, you can see that we're getting that idea of just C. So let's look at a couple of examples and then we'll be done. Before I start, I'll mention my random thing. I have to figure out what I want to do with these. Found something in my fridge that it's little googly eyes that I used for some Rice Krispie treats that I made over Halloween. They're like sugar. Not sure if they're still good. So random thing for the video quiz, be aware. All right, so to be honest, it's a little bit easier to do total displacement because it's exactly what you would think. It's integrating over the limits of integration from 1 to 6 of your function, the velocity function here, minus 8. And in this case, we are talking about dt. So don't forget that you want to be thinking about dt because that's what the function is. And then you're just integrating. So you can pause if you want and see if you can get the answer. Your answer should be a number, and then come back and check it. So we take our antiderivative, we just plug in our values and see what we get. And it looks like if you do this, you're going to get a negative 3 1/3. Okay? So this idea would be the particle moves 3 1/3 meters to the left. Like basically that's where it ends up at the end of whatever it's doing from 1 to 6. And then the last question here is total distance traveled. So in order to find this, because this is a different answer, we have to think about where the velocity might change. Because as you can see from the picture towards the top of the page, whenever the velocity is negative, you know, there's a place where it's crossing the axis, and we need to come up with basically those places where that velocity may cross the axes in order to find the intervals of positive and negative velocity so that we can then create multiple integrals. So we'll have this equaling 0, and typically these factor, I mean, it's not surprising when they do. We get t equals -2 and 4. And so we also know that we're going from 1 to 6. So understand that basically what we're being told is that we start at 1 and we end at 6. So we don't need this. This is not in the interval, not in the interval. Time is not negative. So the 4 is the important value. And you can see just by thinking about t squared minus 2t minus 8, when is it greater than, less than 0, something like that. If we think about really, I mean, this starts at 1 and then 4 and then it ends at 6. If you were to put in a value like 2, you can see that you're going to have 4 minus 4 minus 8, so it's going to be negative. And then you're going to have, say you put in 5, you're going to have 25 minus 10 minus 8, so that's still going to be positive. Okay, so this tells us stuff. in terms of what our intervals should look like. So when we then think about from 1 to 6 doing this absolute value of t squared minus 2t minus 8 dt, what that's going to look like is, what you want to understand is from 1 to 4, you're going to have a negative area, but for total displacement, we want the positive value. So we're going to integrate from 1 to 4, and we're going to take the negative of that. So t squared minus 2t minus 8 dt. Okay. And then we're going to add to that, I'll just move it down a little bit. We're going to go from 4 to 6. Now we already know that velocity is positive there, so for that function that's going to be above the axis. This is the original function, and so that tells us that we just have it the regular. We don't have to make any changes to that, so it's just going to be t squared minus 2t minus 8. Now, these are the same antiderivative. They're even the same antiderivative we got in the last one. We really just have to think about the evaluation of what we have. So you're going to have I'll put the negative here, t cubed over 3 minus t squared minus 8 from 1 to 4. And then we have regular t cubed over 3 minus t squared minus, oh, sorry, I need an 8t, 8t, there we go, and that's going to be from 4 to 6. And then it's just evaluating and seeing what you have. Notice you're going to have, both of them have the 4, but one of them is the negative, and so that can possibly change what those numbers are going to look like when you plug in. So let's see how far I want to go with this. Okay. So again, you can pause, you can see if you can get it. Okay, so I'm going to have a negative, and then I'm going to have 64 over 3 minus 16 minus 32, and then a minus, but I have a minus here. So it's already subtraction because of the fundamental theorem part 2, but then I have this minus right here. So then that'll be a plus, and I'll have 1/3 minus 1 minus 8. Okay. Then over here I have my second integral, and I'm going to put in 6, so it should be 216 over 3 minus 36 minus 48. Great. And then subtract what we get when we put in 4, which we already know, 64 over 3 minus 16 minus 32. But notice positives and negatives there, so you do have to pay attention. And then once you do all these things together here, let me just double check my values so that I know I'm giving you the right thing. Okay, and all right, everything looks good. Okay, you combine that all together, you should get a 98 over 3 meters, which is 32 2/3 meters. So you can see the difference for sure between displacement and distance. That distance is going to be combining all of the travel that's done, whereas displacement is thinking about where somebody ends up, or something, particle ends up, at the end of the time interval. And that's section 4.4.